Hello, everyone. I have responses for you for the potential energy diagram questions. Listen to my answers and explanations, and then after we've gone through the 30 of them, email me your questions or post them online. I read my posts and my emails because I get back to you all the time. And, we'll go from there. Maybe on Monday, I'll deal with the questions that popped up over the weekend and then go on to the next lesson. Okay, here we go. Starting with question number one. The reaction diagram posted, okay, that's an endothermic because A and D are lower than G. So that's going uphill. It tells you to go to reference table I. That's the delta H table. When you turn to table I, go to the eighth one from the bottom. The bottom one says H plus OH yields H2O. That's the net ionic equation for neutralization, by the way. And we go eight up 1, 2, 3, 4, 5, 6, 7, 8. You come to one that says H2 plus I2 gives 2HI. And if you look at the delta H value, it says positive 53. Since it's a positive value, it's endothermic. If you looked up the other choices, they'd be negative, which many of you would have said, oh, 3 negative, 1 positive. It has to be the one that's different. You'd be right because it can only have one correct answer. But just to tell you a little bit more how that works, that 53 for every H2 or every I2, you get two HIs. The two HIs give you 53. That means one HI, if you ever get asked a question like that, one HI would be half of that, which would be 26.5 positive for one HI. And that would require a half an H2 and half an I2. But be that as it may. All right, question number two. In the chemical reaction, the difference between the potential energy of products and reactants, that's the heat of reaction, D. Question number three, the potential energy diagram is shown below. Each interval on the x-axis is 40 kilojoules. So I'm going to put some numbers on my axis. The bottom one is going to be 0, then 40, then 80. So where the reactants are is 80, and then 120 where the products are. 120, 160, 200, 240. Just for the sake of arguments, the potential energy of the activated complex is 240. It says each interval is 40. What is the heat of reaction? It's going to be 120 minus 80. 120 minus 80, which is 40, positive 40, right? Because it's products minus reactants, or it's endothermic and it's positive. So you can say, oh, the difference between the two is one interval, which is 40. If it was going down 10, it would be negative 40. Since it goes up 10, it's positive 40. Or you can do delta H is equal to the heat of products minus heat of reactants, which would be 120 minus 80, positive 40. Okay, showed you that formula yesterday. Question number four. It says which interval on this diagram represents the difference between products and reactants? That's interval 4. I'm going to tell you the other intervals. Interval 1 is HR, potential energy of the reactants. Interval 2 is potential energy of the activated complex. Interval 3 is an activation energy, but that's reverse. Oh, actually, no, I lied. It's forward because it is the forward height. That line 3, we would normally draw it all the way over to the left. It doesn't go down to the product height. So interval 3 is forward activation energy. But the answer was D4. All right, next page. Given the potential energy diagram, which statement correctly describes it? The activation energy, okay? They ask us about activation energy, and they ask us about is it endo or exothermic? Okay. The activation energy is from 40 to 50, right? It has to go up 10. The activation energy is 10. Since it starts high and ends up low, it's exothermic, right? Just for the sake of it, I'm going to calculate the delta H for this one. the heat of the product is going to be 15 minus 40. That's going to be negative 35. See how it comes out to be negative when it's exothermic? Okay. So delta H is negative 35 for that one. 15 minus 40. Number 6, circle the word energy in the equation. It's on the right, so it's exothermic. There's only one exothermic choice. That's A. Number 7, the activation energy required by a reaction can be decreased. C, adding catalyst. Catalyst lowers the height of the hill. So the hill becomes lower when a catalyst is added. 8, all right? Underline the words in the middle of the question that say gases react explosively. An explosive reaction is an exothermic reaction. B shows an exothermic reaction. All right, potential energy diagram shown below. Which letters represent the activation energy of the forward and reverse reactions? B is forward, C is reverse. So the answer would be C, B, and C. And A is heat of reactants or potential energy of reactants. We would label that HR. And D would be HP. All right, the answer for number 9 is C, B, and C. 10 and 11. Excuse me. Which numbered interval will change with the addition of a catalyst? Catalyst lowers the height of the hill. So at the very top of the curve, can you see this? At the very top of the curve here, this is where the activation energy would normally go. But now it would be down here where I've drawn that little line. So interval 2 would be the one decreased. It changes and lowers the activation energies. So it's choice B, 2. Number 11. Which statement correctly describes the reaction? It's an exothermic, and exothermic releases energy. So that's D. We know it's exothermic because where 4 is, the product is lower in height than where 1 is. Right? So if from start to finish, left to right, it goes down. Number 12. Well, I think we did this one in the textbook. The answer is 20. I think it was in the textbook. I'm almost 100% sure because it's very familiar to me. Number 13. Okay. Delta H is 7.9, okay, in the production of 2 NO2s, okay. That's that interval 2, by the way. So that's going to be 7.9 units of energy, okay. Which arrow represents the heat of reaction for the reverse reaction? It's still interval 2. The only difference between forward and reverse activation energies, they're the same thing. Not activation energy, sorry. The only difference between forward and reverse delta H's is that one is positive, one is negative. In this one here, for the forward, the way it's written, it's positive 7.9. But in the reverse, you're starting high and going lower. That's going to be negative 7.9. Right. Number 14, this too was in our book, so you should find it easy. The answer is A, the forward catalyzed reaction. Number 15, given the potential energy diagram, it's going down overall. So it's exothermic, and exothermic has negative delta H's. So that's D. Number 16. Oh my God, this is a complicated one. Actually, not really that complicated. It's confusing the way it's worded. The question itself is no more difficult than any of the others. It's just worded. The choices are worded funny. It says the potential energy of the activated complex is the sum of what lines? Well, it's going from the absolute bottom to the absolute top. Okay? So you got to find 2 lines that you can put together that get you from the absolute bottom to the absolute top. Like, for example, this is not a choice, but it could be y plus 30 plus x. Y plus 30 plus x would do it. Not a choice. W plus x, hey, that will do it. That's a choice. That's choice B. Or y and z would do it. That's not a choice. Okay. Finish that page. Number 17, the graph below represents a potential energy diagram. Where is the activated complex B? It's the top of the hill, as I said yesterday. Okay. Number 18, given the balanced equation, N2 plus 3H2 gives 2NH3, right? Which statement is true? The 91.8, the energy is on the right. That means it's going to be an exothermic reaction. It's exothermic. And when it's exothermic, it's negative, so it's A. Number 19, given the balanced equation, it's actually the same thing. It's D, right? The energy is on the right, indicating exothermic. Exothermic is negative. All right. This is one that I kind of alluded to with problem number 1. It's actually mole related. Heats. The more stuff you burn, the more heat you release. If you burn 1 mole of a gas, you'll get so much heat. If you burn 2 moles of the gas, you'll get more heat. If you burn 3 moles of the gas, you'll get more heat. 4 moles of the gas, more heat. 5 moles, you get the picture, right? I'm being a little ridiculous here. But okay. So when we look to the equation as provided, it says 571.6. 571.6. But when you look to the balanced chemical equations, what's the coefficient in front of water? H2O. It's 2. Coefficient of 2 in front of the H2O. So 571.6 is for 2 waters. So for 1 water, it's going to be half of that, which is the 285 value. Now the question is it positive or negative? It's going to be negative because it's on the right and it's exothermic. So the answer is A. All right. If you have questions on that, post them and I will respond. Number 21. What is the heat of formation in kilojoules? Like you see in the question, it says kJ per mole. That's kilojoules per 1 mole. In the equation, there's 2 NOs. So again, this is a case where we're going to be cutting it in half. So it's going to be the 91 number. Now it's got to be positive or negative. Which one? Since the heat energy is on the left of the arrow, that indicates endothermic. So it's positive, and the answer is C. And if you turn to reference table I think this one is on there. The N2021. Yeah, it's about 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the 10th one down. It shows that it's positive there, right? It's positive in that 10th one down. The thing is, it's half of it, so we got to divide it by 2, right? Because it's per 1 mole. The equation uses a coefficient of 2 in front of the NO. Okay? All right? Onward. Okay, part 2 problems. Right, some of these I'm going to have to draw. Okay, a lot of words, blah, blah, blah. Let's get to the question part. On the labeled axis below, draw a potential energy curve for the reaction represented by this equation. We have 2 types, endo and exothermic. Energy is on the right, so it's exothermic. So how are we going to do this? All right. You're going to see my Punnett squares. I did a forensics lesson a little earlier. We're talking about blood types. So I got to erase that. I probably should have erased it before I started, but I didn't. I'll do it now. Okay, bye. Here we go. All right, clean my board. Oops. Take my marker. Okay, here's my reaction coordinates. If it's exothermic, the word energy was on the right. I have to start high, need an activation energy hill, and go lower. There's no numbers on here, so how much lower you go, it's fine. If I want to drop it all the way down, I can. If I want to end it here, just long as the end of it, the product side, is lower than the reactants, and that's fine. All right. Number 23. I'm going to go to the question part again. It doesn't mean that you shouldn't have read the rest of it, because sometimes there are clues in it, but I I kind of looked over these a little bit, so I know. And then underneath the reaction provided itself, that's the light reaction for photosynthesis. It says state evidence that indicates photosynthesis is an endothermic reaction. That means you need to find something physically in that reaction that says it's endothermic, and circle the words light energy. Energy is to the left. Remember, there's a lot of different sorts of energy. Most of the time, energy we talk about in chemistry is heat energy. This time it's light. So the answer, the light energy or the energy is on the left, indicating it's endothermic. All right, number 24, describe how a catalyst, an enzyme, speeds up the reaction. I'm just reading the question under the reaction provided. All right, lowers the activation energy. Lowers the activation energy so the reaction can happen more easily. 24, right? This really could have been a multiple choice one. There's really no reason to have it as a part two, but whatever. Which potential energy interval in the diagram represents activation energy for the forward reaction? The activation energy for the forward reaction would have been letter B. It has to be from the reactant height to the top. And no matter where it is with respect to its left to right progression, it would still be the same. I have an exothermic one here. So just let me show you. In the one that's here, I'm going to draw the lines that help us find everything, right? These are lines that help us find something. It has it here as B, but it would still be B if it's over here, and it would still be B if it's over here. As long as it's from the reactant height to the top, it's forward activation energy. 26. On the potential energy diagram, on the same diagram, draw a dashed line to indicate how potential energy changes when the reaction is catalyzed in the converter. Wait a second. The potential energy diagram shown below shows a reaction 1 without a catalyst. On the same diagram, draw a dashed line to indicate how potential energy changes when a well, it doesn't change the potential energy of products and reactants. It just changes the activated complex. So I'm going to use my same one, which is also exothermic. And remember, it's just going to lower the hill. So the hill is going to be lower. So I'm just going to draw a dashed line to show what it would now be. Anything that's lower than that, the catalyst makes it lower. That was 26. All right. On the potential energy diagram, draw an arrow to represent activation energy of the forward reaction. It's the same thing. It's B, anywhere between the top two lines, anywhere you'd like to draw them. On the diagram below, draw a potential energy diagram for this reaction. Aha, now we got a different one to work with. Usually they show exothermic reactions because I think exothermic reactions are more common in nature. Things would rather lose energy than gain them. That's actually going to be part of this. It's something called entropy. We'll talk about entropy towards the middle or end of next week. All right. Endothermic, here's my reaction coordinates. We have to start lower. We still have our activation energy, and we got to come down. And, where these are, as long as this one, the P1, is higher than the R1, as long as P is higher than R, it's right. And 29, determine the amount of energy released when 2.5 moles of propane is completely reacted. Okay? This is where we do have to go back to the beginning information. If we go back to the very top, it says there's a balanced chemical equation, C3H8, that's propane. I made hamburgers yesterday, so I use propane. C3H8 plus 5O2 gives 3 CO2s and 4 waters, and 22.19 amount of energy is released, right? So if I'm going to get 2.5 moles, I have to multiply that by 2.5. So it's going to be, click my pen, 2219 times 2.5. And then I think we get for an answer, is it like 5,500, 5,550, or in that neighborhood? I think. All right, can you see that? 2219 is provided in the equation by multiplied by 2.5 moles because it's 2219 per 1 mole. And then we get 5,550. I didn't leave myself a calculator. I'm pretty sure that's right. If not, someone will tell me and I'll correct myself in the future. And on the diagram above, draw the potential energy diagram for this reaction. We're just drawing another exothermic one. I'm just going to sketch one out. Actually, I'll do it in a marker so you can see it. Ta-da! All right. I hate going over 20 minutes because these things take so long to upload, especially during the day. When I've done them in the evening, it's gone a lot faster. One person did shout out that they had a question on 12 and 14, I think it was. So I do want to, I actually responded in a post to them, but I just want to review those answers here as well. All right. Number 12, which numbered interval will change with the addition of a catalyst? Interval 2, remember the height comes down lower. So only the highest point lowers. The hill is still there, so only interval 2 would change. 1, 3, and 4 would remain the same. Catalyst just lowers the hill. It doesn't take away the hill, it lowers the hill. And number 14, which arrow represents heat of reaction for the reverse reaction? Well, 2 is heat of reaction. It's also heat of reaction for the reverse. The only difference is, in this one, reverse would be negative, forward would be positive, but it's still the same interval. Okay. Stay safe. I hope all of you are happy and well and not too bored. I'm a little bored. This is cool. It keeps me busy, but I think I'd like to be back in the building, and I hope most of you feel the same. Take care. Be great. I'll talk to you on Monday. Have a wonderful weekend. It's actually pretty sunny out right now. Hopefully, we'll get a little bit of nice weather and go out in our yards and social distance. We'll elbow hello to people and junk like that. All right. Take care. Bye.